We have completed our discussion on elementary continuous time signals, and now we will be moving on to the elementary discrete time signals. The first elementary discrete time signal is a unit step function. A unit step function u of n can be written by the condition as 1 for n greater than or equal to 0 and 0 for n less than 0. That means it will be 1 for all the positive values and 0 for all the values less than the 0th point, n equal to 0 point. Unit ramp function. The second one is the unit ramp function. It is represented as r of n is equal to the discrete time unit ramp function is represented by the letter r of n. The condition for satisfying it is r of n is equal to n for n greater than or equal to 0 and 0 for n less than 0. As we can see here from the point of n equal to 0, it is increasing linearly. The r of n in terms of the step signal u of n can be written by the formula r of n is equal to n u of n. Unit parabolic function. A unit parabolic function is represented by the letter p of n. The signal p of n can be written by the condition which is equal to n square by 2. P of n is equal to n square by 2 for n greater than or equal to 0 and 0 for n less than 0. In terms of the unit step signal, the p of n can be written as p of n equal to n square by 2 u of n. Fourth one is the unit impulse function. The discrete time unit impulse function is otherwise known as a unit sample sequence. It is represented by the letter delta of n, where delta of n is equal to 1 for n equal to 0. When n is equal to n is equal to 0, delta of n will be 1 and 0 for n not equal to 0. Properties of discrete time unit impulse function. We have already discussed the properties for the unit time continuous time unit impulse function. These are the properties for the discrete time unit impulse function. The first one being delta of n is equal to u of n minus u of n minus 1. That is the unit step signal minus the delayed step signal, that is delayed by a point of 1. Second one is delta of n minus k is equal to the delayed unit impulse signal delta of n minus k is equal to 1 for n is equal to k and 0 for n not equal to k. Third one is that x of n is equal to summation of k is equal to minus infinity to infinity x of k delta of n minus k. In case of the discrete time signals, instead of integral as in the continuous time signal, we will be using summation, because we are taking into consideration of discrete cases or distinct cases. Summation of the fourth property is summation of n is equal to minus infinity to infinity x of n delta of n minus n0, which is equal to x of n0. Fifth elementary signal is a sinusoidal signal. The general form for a discrete time sinusoidal signal is written as x of n is equal to a sin omega n plus phi, where a is the amplitude, omega is the angular frequency in radians, phi is the phase angle in radians, and n is the integer. As it is a periodic signal, the time period represented by capital letter N can be written as n equal to 2 pi by omega m, where n and m are integers. The graphical representation of a sinusoidal signal in the discrete way is shown here. A real exponential signal. General form for a real exponential discrete time signal is written as x of n is equal to a raised to n for all n. This also has four main cases. Here, as x of n is equal to a raised to n, when a is greater than 1. A is greater than 1 means a is positive. Then this signal goes on increasing. This exponentially increases. Second case is when the second case is when a is between 0 and 1, that is 0 less than a less than 1. Here in this case we get an exponentially decreasing signal x of n is exponentially decreasing in this case. Third one is when a is less than minus 1, that is it is a negative value, a is a negative value, and when x of n is equal to minus of 1, a x of n is equal to a raised to n and a is less than 1, we get alternating positive and negative signals, and it is an exponentially, but even if it is alternating, it is exponentially increasing in this case. The fourth one is when a is between minus 1 and 0, minus 1 less than a less than 0. Then we get similar to that of the third case, that is we are obtaining an alternating positive and negative signal. It is also, but in respect to this, here it will be exponentially decreasing. Here it is exponentially increasing, here it is exponentially decreasing. Complex exponential signal. The general form for a complex exponential signal in discrete time is written as x of n is equal to a raised to n e raised to j into omega 0 n plus phi, which is equal to a raised to n cos omega 0 n plus phi. That is the Euler's formula is expanded here, which can be written as a raised to n cos omega 0 n plus phi and j a raised to n sin omega 0 n plus phi. The two cases are when, okay, if we consider this a raised to n as, or mod a is equal to 1, if we consider mod a equal to 1, then the real and imaginary parts of the complex exponential sequence, they are here. If mod a is equal to 1, then the real and uh, imaginary parts of the complex exponential sequence will make it a sinusoid. A sine waveform is obtained then. If mod a is greater than 1, if a is greater than 1 and x of n is equal to a raised to n e raised to j into omega 0 n plus phi, then in the positive case, we obtain an exponentially increasing sinusoidal signal. The second case is when a is less than 1, that is a is negative. In this case, the sinusoid will be exponentially decreasing. That's it with the complex exponential signals in the discrete domain case. Thank you.